Well, before we look at SimGEN's new spoofing feature, let's first consider what is spoofing. Well, under normal circumstances, your device will receive the GNSS navigation signals from satellites in space orbiting the Earth. And from these signals, your device is able to determine exactly where it is, both in time and space. What a spoofer attempts to do is confuse your device and make it think that it is somewhere else or at some other time, so that your device is not able to compute its true position. And the spoofer transmitter generates signals that contain information about fake satellites in the sky or fake navigation information about the satellites that are currently being navigated from by your device. And in whatever way the spoof transmitter attempts to deceive your device, the ultimate aim is to make your device think that it's in a completely different position and or at a different time to its true position and time. And so we're going to now look at the way in which SimGEN offers controls to you as the user to add in the spoofing simulation. So here we have our SimGEN scenario, and it's a basic scenario that you would get if you create a new scenario from SimGEN. It's a single vehicle with single antenna, GPS L1 signal types to begin with, and those GPS signals are defined by the GPS constellation sources file here, and these represent our truth situation. It's our device under test, its current global location, and the real satellites in orbit. Now, to add spoofing into the scenario, we simply add that as an extra signal type to our device under test antenna. We double click and we can choose spoofing on that vehicle antenna. And when we do that, we get a new group in the scenario tree called spoofer. And this allows us to define a couple of things related to the spoofing signal. First is our spoofing transmitters, or our spoofer sources. These are the transmitters that will broadcast the fake GNSS signal, or the spoofing signal. And those signals represent the satellites in the sky, and to define what those satellites are doing, we have a constellation file which is unique to the spoofer, so it's completely independent to the truth constellation that we just had a look at. And then finally we can define a fake location that we want our device under test to be fooled into thinking is its real location. Okay, and in much the same way as our target vehicle, our real device under test, we can give this spoofed location a static position, or we can give it some motion using one of the built-in models in SimGEN, or we can even send some real-time motion from a remote source. We're going to stay with static conditions to begin with, just as we explain how the spoofing configuration affects the layout of the scenario. But here in the ground track, where we started with just our real vehicle, we've now got the location of the spoof vehicle in view, the spoof transmitter. And if we zoom out, we can now see that we have a duplicate set of GPS satellites. They're indicated with this /S1, which is, in this example here, satellite number 8 from spoof constellation number 1. Now these are the default conditions. By default, the truth constellation shares the same file as the spoof constellation, and the spoofed vehicle position shares the same location as the true vehicle location. But what of course we want to do is modify those conditions so that we're looking at completely different things. And so we'll take a look at how we do that now. So let's start by looking at the spoofer transmitters signal sources file. We'll double click to open the dialog, and this allows us to specify how many spoofer transmitters we want in the scenario, how many sources of the fake GNSS signals we want to include in the scenario. And SimGEN allows up to 64 transmitters. Now you have to be careful when you define how many transmitters you want, because you need to be aware that a single spoofer transmitter can be responsible for multiple satellite signals. Now in Spirent's product, one satellite signal uses one signal generator channel. And we can see this here using the power levels display. Here we have our truth GPS signals. And to begin with, I've got a situation with a single spoofer transmitter, and that one spoof transmitter is providing a fake GNSS signal which consists of the same number of GPS satellites that I have for my truth signals. It happens to be the exact same set of satellite SVIDs, because I'm using at the moment the same underlying constellation file. But you can see that we have 10 truth satellites in view, and those same 10 satellites from the spoof constellation. Now this means that I need 10 channels just for my one spoof transmitter, or my one spoof signal source. So you need to be aware of the system that you have purchased, how many channels you have for each different signal type that is going to be allocated for spoofing signals. Now of course you don't necessarily have to have all 64 spoofing transmitters in view at the same time. You may have a complex array of these transmitters laid out over a wide area, and your vehicle is going to be moving through that area, and at any one time perhaps only 2 or 3 transmitters are in view, and therefore you only need to worry about how the maximum available channels will be divided evenly between those spoof transmitters in view. So what I'm going to do, just for the sake of this demonstration, is I'm going to add a second spoof transmitter, and we're going to just take a look at what happens. So I increase my number of transmitters to 2. I then define where I want to position these 2 transmitters, either relative to the vehicle start position, or I can give them an absolute position, and depending on which setting I choose will then influence which of these 2 pages I can go on to complete. We're going to use vehicle relative for now, and what I'll do is I'll just simply put what I've got. The first one here is just north of our true vehicle, and so for the second one I'll just place it to the east. Let's just make it slightly closer. We'll leave the height the same. The other general setting I use is with respect to the transmitted power from the spoof transmitters. Do I want to use model power, which will mean that SimGEN will automatically vary the received spoof signal level as the distance between my target vehicle and the spoof transmitter changes? Or do I want to use a fixed level, which means that regardless of the distance between the spoof transmitter and my target vehicle, my device under test, I will always simulate the same received spoof signal. For the fixed setting, you are simply defining a spoofer gain. Now, if we just again look at the power levels graph, in this example, the spoofer has a gain of 4 dB, which means that the satellite signals are received just 4 dBs hotter than the normal truth GNSS signals, and we'll kind of come on later as to why that is. But again, in this simple default situation, spoof signal level, which is 4 dBs gain, will just simply increase the GNSS signals, spoofed GNSS signals, by 4 dBs relative to the truth signals. With model power, you have a similar situation where you can just simply specify the gain, or you can go about it by saying at what distance from your device under test, your target vehicle, you want the target vehicle to experience 0 dBs of gain. In other words, how far apart is the vehicle and the spoof transmitter when the vehicle will experience the same signal level from the spoof satellites as it is receiving from the real satellites in space. Now, for this example, just to demonstrate what the effect of model power will do, as you know, we've just set up 2 spoof transmitters. One is 800 meters east of the vehicle, the other is 1,000 meters north of the vehicle. So what I'm going to do is, having chosen model power, I'm just going to say that 0 dB gain is when I am 800 meters from the vehicle, and SimGEN automatically calculates the free space loss for an 800 meters range and what transmitter gain you would otherwise need to achieve that. I'm just going to click all, so both my spoof transmitters are transmitting at that level, or I can use completely separate values if I want to. Okay, so we'll just call this 2 spoofers. So here in the ground track, we can now see we have this first spoof transmitter, which was 1,000 meters north of the truth vehicle, the target vehicle, and a second spoof transmitter, which is 800 meters east of the vehicle. And in the power levels graph now, we have these 2 spoof transmitters, and as explained, we've set them to have the same transmitter gain, which would mean 0 dBs of gain when you are 800 meters from the vehicle. Spoof transmitter 2 was precisely 800 meters away, which is why its transmitter gain is 0 dB, and spoof transmitter 1, which is a little bit further away, SimGEN's automatically calculated what the respective gain of that transmitter is, which happens to be -2 dBs, with it being just that little bit further away. And you will also notice that what takes place here is that we now get a duplicate set of satellite signals, one set for one spoof transmitter and the other set for the other spoof transmitter. And the way this works is very simple. GPS/S1 is telling us the spoofer constellation that's involved. In this case, we've just got the first spoof constellation. And then we have an ID number, which is the satellite number, number 7. And then we have a spoofer transmitter number, which is the source of that satellite signal from that spoof constellation. And if we look along here, we've got pairs of satellites, one for spoof transmitter 1 and one for spoof transmitter 2. And as a consequence of that, it's now requires us to have 20 available signal generator channels in order to simulate all of the satellites from both spoof transmitters that are in view of the vehicle. If we didn't have that many channels available, then we would simply see a limited quantity of spoofer satellite signals. So now we're going to move on and take a look at how we can define the spoof satellite constellation. So let's take a look in the spoofer constellation file. And the dialog editor is exactly the same as you would get for your truth constellation. We have all of the controls over the satellite constellation here, and perhaps a couple of key areas to highlight will be the navigation errors and modifications pages, where we can insert changes in the navigation message for particular satellites in view if we want to attack the target vehicle in that way. We can alter the message sequence for the CNAV, in this case on GPS. We may want to specify completely different orbits. Perhaps we want a totally different set of satellites in view compared to the truth signals. Maybe we want to move one of the satellites very slightly on its orbit, and we can do that through this control. And we may want to load a completely different almanac if we're considering a meconing event, a recording, a replay from perhaps several hours previously or days previous, and we can configure that constellation from that time here. We may want to add errors on these spoof satellites that are not present on the true satellites. Equally, clock errors we can add in here. We may want to add or remove signal content. We may want to change the PRN of one of the broadcasting satellites to try and fool the receiver into thinking that it's something is going on. We may want to have satellites going on and off at different times during the run. Again, all of these things are possible and completely independent of the truth constellation, and that's the beauty of this control, is that you can treat it as if it's a real constellation in its own right, and SimGEN will take care of the consequences of the changes that you make directly. Now we're just going to do a very simple example here, where I'm going to cause the spoof satellites in view to be totally different to the true signals, and I'm just going to do that by modifying the orbital reference time of the satellites. There is another way to achieve the same, which we'll look at in a moment. So let's move this by 5 hours, let's say. So I'm just going to change that time by 5 hours. Now this is possible because I'm using SimGEN's default orbits, which are nice regular circle orbits. You see the eccentricity is set to 0 here. If I was using a real almanac, pushing the reference time too far would lead to certain orbital modeling errors as SimGEN tries to extrapolate the orbital parameters to the new reference time. But in this case, I'm safe to do that. So we're just going to have a simple name, different orbital reference time. Okay. And if I zoom out on the ground track display here, then what we should see is that the in-view satellites are in completely different positions, whereas before they were perfectly co-located. I'm just going to zoom in and so you can take a look at a couple of examples. Okay, so the satellites with the S1 are our spoof constellation, and the satellites with no suffix are the true constellation. You can see there's completely different orbital arrangement taking place here. and then that's also replicated in our power levels graph. We no longer have the matching set of truth satellites and spoof satellites, but our two spoof transmitters are still taking care of the same set of satellites. So what we currently have taking place here is a set of truth GNSS signals that represent our truth vehicle position, and two spoof transmitters providing spoof GNSS signals that represent the spoof location. At the current time, our spoof vehicle and our truth vehicle are co-located, and so your device under test would simply get a different set of information from the spoof satellites, but representing the same location, which of course is not necessarily going to achieve what we want. So what we want to do now is take a look at how we can give the spoof vehicle a completely different location, and therefore begin to really fool the target device into thinking it's somewhere that it is not. So we're now going to use the spoof vehicle setup to choose a location to fool our device under test into thinking that that is where it really is. As we said earlier, you can define one of the standard vehicle types that SimGEN offers. I'm just going to choose the simple motion for this example, and I'm going to create a circle which travels around the current truth vehicle static location. So I'm just going to give it some settings here for the vehicle, the circle radius and the vehicle speed, just arbitrary values. And what's going to happen now is the spoof transmitters and the GNSS satellites that are part of the spoof constellation, they are going to represent the motion of this spoof vehicle. So pseudoranges will be automatically updated from those spoof satellites, which represents the pseudorange to the spoof vehicle, whilst the truth satellite signals will involve pseudoranges which represent the static truth vehicle location. And so obviously the purpose of the test would be to try and achieve a situation where your device under test begins to navigate from the spoofed satellites, and as a result make it believe that it's moving in a circle rather than sitting static in one location. So I'm just going to press play on the scenario now, and we can see the spoof vehicle in motion. The target vehicle is static. We've got updated pseudoranges from the spoof transmitters, the truth satellite signals, and if we were to be able to observe this at RF with a receiver connected, what we would hope to see is that the receiver's own navigation solution begins to move away from the true position and begin to think that it's traveling in a circle. So this is a very simple contrived example. We can get more complex with this, and we can also position these spoof transmitters so that as the vehicle moves, it can move in view and out of view of each spoof transmitter. But in essence, this is the principles of the spoof vehicle setup, so that your target device begins to move on a trajectory or to a different fixed location that is different to its intended true location. So I've shown how we can add spoofing signals into the scenario, how we define the spoof transmitters, the spoof constellation, and the corresponding spoof vehicle location that we want to simulate. But what if we want a more complex scenario? What if we want multiple transmitters to represent different spoof vehicle locations or different satellite orbital conditions? Well, we can do that by adding additional spoofer groups or spoofer constellations when we specify the device under test or the target vehicle's antenna signal types. And let me use an example of 4 spoof constellations. So now here in the scenario tree we have 4 groups for the spoofers, and each one allows you to uniquely set conditions for the transmitters that are responsible for each definition of spoof constellation and spoof vehicle position. Now you have to obviously take care with respect to how many channels your equipment can support. As we explained earlier, for one spoof transmitter you will potentially simulate multiple satellite signals, and for each spoof transmitter that you add, you're going to need to multiply the number of available channels. So now that we have multiple spoofer groups, specifying multiple spoofer transmitters for each group will quickly use up the available simulated channels. Now again, you may wish to define a complex scenario where no spoof transmitter is in view of another, only a single spoof transmitter is in view of the vehicle at any one time, so you preserve the quantity of simulated channels for each spoof transmitter as it comes into view. But that really depends on your needs and the configuration of your test. What's important is just to keep that in mind, that for example 2 spoof transmitters for each of these spoofer groups that we now have will mean dividing up, for example, 16 simulated channels 8 different ways. That means that only one spoof transmitter can be responsible for 2 satellite signals if they were all in view at the same time. So let's just look at a very simple example where for each of these spoofer groups I'm going to specify a single spoof transmitter, and we're going to I've got some files set up for this just to simplify the time it takes to create the scenario. We're just going to lay them out. Each of these spoof transmitter files specifies also modeled power and an absolute position. I'm going to give each, I'm going to just keep the same default constellation for each spoofer group for now, but we're going to choose some different type of vehicle motion. Let's quickly throw that in here. So we've got some circular motion. Some simple aircraft-based motion, so flying vehicle. Let's go with a land-based vehicle. And let's add another circular motion. Okay. Now all of these 4 spoof transmitters are in view at the current time. So here in my received signals power levels graph, I have the 4 spoof transmitters, and because of their different positions relative to the vehicle, its current position, and because I've used modeled mode, we're getting slightly different power level gain, which corresponds to slightly different received satellite signal levels for each of the spoof transmitters. Now I should explain that because each spoof transmitter is now responsible for its own spoof constellation, here in the power levels graph and in other displays, we've actually can see that we have spoof constellation 1 for the first set of channels, and then we have spoof constellation 2 for the next set of channels, so forth for spoof constellation 3 and 4. And in my configuration, I have an availability of 32 channels for my spoofing, which is why each spoof transmitter has been allocated 8 channels of satellites. And compare that with my truth constellation, which has the full potential of 10 satellites in view. So I'm losing a couple of satellites in view to my spoof signals, but I still got a good quantity of 8 in order for my test to take place. I'm going to just move the truth vehicle position as well, just for the purpose of this demonstration. And what I'm going to get this vehicle to do is just fly through and between these spoof transmitters. The spoof vehicle motion is going to take place in and around my truth vehicle, just to kind of give you a flavour for what's possible with SimGEN and simulating multiple spoof vehicles, all with their own independent trajectories, broadcast signals from multiple spoof transmitter locations. And what's important is that modelled power is influenced by the relative position of the truth vehicle to the spoof transmitter, not the spoof vehicle position. But the spoof satellites that are visible are with relation to the spoof vehicle location, not the spoof transmitter or the truth vehicle. And so we can see model powers changing from these spoof transmitters as the vehicle moves past each spoof transmitter. And of course, if we had a receiver connected to our simulator, it would see influence from one spoof transmitter more so than the other as signal levels increased and decreased. Now, my truth signals remain reasonably static in level, and that's because in terms of the distance I've travelled with my truth vehicle relative to those real satellites in the sky, there's very little change taking place. But the more rapid changes of the spoof satellite signals is as a consequence of the changing range between each transmitter and the vehicle, the target vehicle. So of course there will come a point when the target vehicle on its true trajectory moves so far away from these spoof transmitters that it's no longer influenced by the spoof signals that they are broadcasting. But in that situation, we would potentially add additional spoof transmitters, which would ensure that the target vehicle is always under the influence of the spoofing signals. One final feature that's available with spoofing in SimGEN is the spoofer start time. And this comes in useful if you're considering a meconning or a repeater event. And you can set the time to match the time of the original signal recording that was performed, and then you're going to repeat that recording perhaps on the following day. Now the satellite signals in that replayed broadcast need to be representative of the day of recording, not the day of the playback. So your scenario time is the day of playback, but your spoofer time is the date of recording. So you can specify this in two ways, either as a fixed start time and date, or by simply offsetting the time ahead or behind the current scenario start time. So let's take an example where we've done a recording at 10 in the evening the previous day, and so I'm just going to use the start time for that. Okay, and that's for spoofer group number 1. Now the satellite constellation, the orbital locations of those satellites will be updated to represent their positions at 10 o'clock in the evening on the previous day. If I say that my scenario start time is now 10 AM. Okay. For spoofer group number 2, maybe I want that to perfectly follow the scenario start time that I'm using. So I'm just going to use the time offset control so that it will always follow changes to the scenario start time. And we see that the spoof groups 3 and 4, because they were default to a fixed time, they're now going to start to drift away from my choice of scenario start time. So it's appropriate just to make sure that you're keeping track of your current settings. If your choice is to only influence one of multiple spoofer groups that you may be using. Just to keep matters simple, I'm going to remove spoofers 3 and 4, and I do that by changing how many spoofer constellations I want. Okay, if we zoom out, then what we should see is that if we take satellite 21 as an example, 21, which is my truth satellite, and 21 from spoof constellation number 2 remain on exactly the same orbital location because they are following the same scenario start time. But satellite 21 from spoof constellation number 1 is now in a completely different sky position because of the fact that we've updated the start time for that constellation. And so if we now run the scenario, we would observe different satellites in view for these two different spoof transmitters. An important aspect of spoofing simulation is to ensure that the spoofed signals appear as if they are coming from the location of the spoof transmitters rather than from the space-based GNSS satellites in the sky, which is where the truth signals are obviously radiated from. And so in SimGEN, with this simple scenario setup, I wanted to show you how that's achieved. So what we've got here is two spoof transmitters. The first one is located just 100 meters away from the vehicle, but it's below the vehicle height. And so that's represented here by that spoof transmitter pseudo range being just over the 100 meters due to the height differences, but at a negative elevation and an azimuth of 0 degrees, as it's directly north of the truth vehicle. What's going to happen with this spoof transmitter 1 is we're going to start the scenario. It's going to move in a circle around the vehicle just to demonstrate the changing azimuth and how that's correctly controlled in SimGEN. And then we've got a second spoof transmitter that's positioned 1,000 meters to the east of the vehicle. That's going to stay static, and we're just going to see that the pseudo range remains consistent and constant at 1,000 meters pseudo range. What's important to note is that the elevation and azimuth of the spoof signals coming from spoof transmitter 2 will remain constant, and with spoof transmitter 1 signals, as the azimuth changes as it moves in a circle, so too will the perceived azimuth of the satellite signals that it is generating. And we're going to use satellite number 5 for this example, just so we can focus on those values. So if we look to begin with, this truth value of satellite number 5, the truth signal here is coming from positive elevation, some position in the sky just off to the southwest, and that's got a particular pseudo range. Spoof transmitter 1 signal here for satellite number 5, it's got the same elevation and azimuth values as the spoof transmitter, and that's what we should expect. The other thing to notice is that the pseudo range between satellite number 5 from spoof transmitter 1 and the truth signal is different by approximately the 100 meters, and that's the pseudo range due to the range between spoof transmitter 1 and the truth vehicle. And then the equivalent is true for spoof transmitter 2's satellite signal, spoofed simulated satellite number 5, and its pseudo range is approximately 1,000 meters different from the truth signal. Okay, so we're going to let this run. What we'll see is that if we can by watch this, that we'll see that spoof transmitter 2, satellite number 5, and truth signal satellite number 5 will always remain 1,000 meters pseudo range difference. Spoof transmitter number 1 and the truth signal pseudo ranges will always remain approximately 100 meters different, because even though we're moving in a circle, it's still going to maintain that 100 meters range offset. But satellite number 5 from spoof transmitter 1, its azimuth will change and follow that azimuth change of the spoof transmitter. Okay, so here we go, and it should be self-evident as the scenario runs. So as we can see, spoof transmitter number 1 is beginning to move in a circle around the vehicle position, and as it does so, its azimuth increases in a positive direction, and so too is the perceived azimuth of satellite number 5 broadcast by spoof transmitter number 1, which is exactly what we expect. Whereas the same satellite signal from spoof transmitter 2 remains fixed in terms of its direction of arrival, and that's exactly what's happening with that static spoof transmitter. Now, of course, this is important if you're testing controlled reception pattern antennas and you want to test that technology and confirm that it's able to detect and correctly mitigate against spoofing transmitters that are coming from certain directions that are clearly not where you would expect true navigation signals to come from.